All right, you guys, we're going to cover section 2 today, bisectors of triangles. I am awkwardly recording this in the solitude of my classroom because I forgot to record it the other day, so if it's a little bit choppy and awkward, I sincerely apologize. So, in section 1, we discussed perpendicular bisectors and angle bisectors, and today we're going to put that into the context of an actual triangle. So let's just first revisit what a perpendicular bisector is. So a perpendicular bisector is a segment that goes through the middle of a line, ray, segment, or point that goes to the middle of a segment and intersects at a right angle. So when we put that into the context of having a full triangle here, I'm actually going to bring up a little picture here and kind of show you how this works. So if I graph a little triangle, I'll just make it something nice and simple here. Right, and then connect those together. There are 3 sides on a triangle, right? So when we talk about what we can do perpendicular bisectors for, we can make a perpendicular bisector for all 3 of those sides. So let's just first look at side A to B here. If I draw in a perpendicular bisector for that side, just that side, and kind of try and ignore AC and CB, that's what it would look like. So you'll notice here, and I wish I had a little pointer, but if you watch my cursor in the middle here, and I can go like this and it makes it bigger, there it is. If you look here, it's going right through the middle of segment AB and then intersects at a 90-degree angle. And I can make that perpendicular bisector for all 3 sides. All right? And then what do you notice? And hopefully if there were students sitting in here, you would say something to the effect that they are all intersecting at a point. And that is accurate. Well, let's just move my triangle around a little bit and see if that is still true if I move my point. So if I move point C, okay, I can move point C wherever I want, and those perpendicular bisectors are still going to intersect. I can move point B, same thing, they're still going to intersect. I can move point A, same thing, they're still going to intersect. So, no matter where I move those points, those 3 perpendicular bisectors are always going to intersect at a single point. And I'm going to go ahead and place a point there. We'll call it D. Okay? We call that concurrency. So concurrent in math is kind of a fancy word for intersection. It's just a little more specific. So intersection is technically just 2 lines crossing. Concurrency is when you have 3 or more lines crossing. I would still accept the word intersection, like you don't have to use the word concurrent in a sentence, but you might see the word concurrency pop up on an assignment or on a test or something. So if we go to those note sheets, concurrent lines happen when 3 or more lines, rays, or segments are intersecting in the same point. And that point that they're intersecting at is called the point of concurrency. Okay, I'm just getting out my notes here to make sure I don't miss anything for you guys. Now, what we just drew were perpendicular bisectors, and those meet at a point that has an actually specific name. So a circumcenter is specifically where 3 perpendicular bisectors are meeting. Okay, so that point, that name is specific to perpendicular bisectors. So if these were a different kind of segment that were not perpendicular bisectors, that word would not be used. Okay, now let's talk about, going back to section 1 here, a property that we learned with perpendicular bisectors. So if I draw here a segment, and it's perpendicular bisector, and I'm just eyeballing, we said in section 1, and again, perpendicular bisecting looks like that, we said in section 1 that any point that lies on that perpendicular bisector, any point at all, including that midpoint, is going to be equidistant away from the 2 endpoints, right? Didn't matter where it was at. It kind of created like this nice little isosceles triangle shape. So now imagine taking that theorem and tripling it, essentially. So in a triangle, you can create at most 3 perpendicular bisectors. In this picture, it's kind of funky because the perpendicular bisectors are not extended all the way through. They're just showing up to the part where it intersects at that point of concurrency, the circumcenter. But if we kind of look here, like if we look at PF, PF is the perpendicular bisector. It's just not showing it being extended all the way through point P and past point F. But it is cutting the segment AC in half and is intersecting at a right angle. Well, point P is a point on that perpendicular bisector. So we learned in section 1 that it's equidistant away from the 2 endpoints. And that's going to be true of all 3 of those perpendicular bisectors. So PE was another perpendicular bisector, as was PD. So point P is equidistant away from point B and point C. And point P is equidistant away from P and A, or from B and A, excuse me. And so whenever you have a triangle, that circumcenter is always going to be equidistant from the vertices of the triangle, so from all 3 corner points. Because again, you're essentially taking that theorem from section 1 and just tripling it. Now, I unfortunately don't have a good example problem of that theorem specifically being used like I should. I only have a couple graphing problems on your note sheet. But you might have some problems on your homework that say, okay, pretend that D to B is 10, P to B is 15, find P to C, right? Well, there's no actual calculations involved there. P to C is going to be the same length as the other red segments. It's going to be the same length as PA and PB whenever you're dealing with the circumcenter. So since PB is 15, PC would have to be 15 as well. That looks like a 13. Hold on. Okay, 15. So that 10 doesn't really get used in that problem. So just be prepared for something like that. Now, let's talk about graphing. Oh, before I get there, I apologize. Location of the circumcenter. So if it is an acute triangle, it's always going to be located inside the triangle. If it's a right triangle, it'll always be on it. And if it's obtuse, it'll be outside of it. So I can go back to my little GeoGebra file here. Currently, I have an acute triangle because all 3 angles are acute. A is acute, B is acute, C is acute. And that circumcenter is right inside. If I move point C over to make it a right triangle, I want you to watch point D. Boom, now it's directly on the triangle, and more specifically, right in the middle of the hypotenuse. Let me make a different right triangle. I'm going to move point B up and make a right triangle. Here we go. Boom, locked into place. It's directly on the hypotenuse. Now, I'm going to extend point B out and make this an obtuse triangle. I want you to watch point D. Here was an acute triangle. Here was a right triangle. Now it's obtuse, and you see point D kind of escape further and further away. So whenever you have that obtuse triangle, those perpendicular bisectors are not going to meet until they're outside of the triangle. So that's just a good frame of reference to have. And I'll let you guys kind of, there's a chart on your notes where you can go ahead and take a minute to fill that in. So again, if it's an acute triangle, the circumcenter is always inside. If it's a right triangle, it's always on it. And if it's an obtuse triangle, it's always going to be outside the triangle. And again, that's just a good frame of reference to have as far as actually graphing a problem and knowing, okay, if it's an obtuse triangle that I've just graphed, then this circumcenter should be outside of the triangle and not inside. Okay. So if you're just sitting here waiting, you can go ahead and start looking at example 1 and get that graphed. And we'll go ahead and find the circumcenter of that triangle. And I might just go through one example. I haven't decided. Let's see. We can skip that. Okay, so if I go ahead and graph and label my triangle here, A is at 0, 3, B is at 0, -1, and C is at 6, -1. this lovely little right triangle. All right? Our directions say find the coordinates of the circumcenter. So they want to know where the circumcenter is at. Well, again, definition here, and this has to be a definition that you're familiar with, because if you have directions on a test that say find the circumcenter, and you don't know what kind of segments you're dealing with, then that's going to be really hard. So circumcenter, you're dealing with perpendicular bisectors. Now, we don't really need to graph all three to see where they intersect, right? We just need to graph two of them, because where two of them intersect, the third one's automatically going to intersect as well. Now, when it's a right triangle that's all lined up nicely like this one on some horizontal and vertical lines, that makes choosing which two perpendicular bisectors to draw pretty simple, because you would want to pick the nice horizontal and vertical lines. So if you see here, side AB is a nice vertical line, and side BC, or AC, excuse me, is a nice horizontal line. Those are going to be two sides of the triangle that are going to be really easy to draw in the perpendicular bisector for. Let's start with AB. So it needs to, first of all, bisect. I like to start there. So it needs to go through the middle. So first start by finding the middle of AB. And this, I mean, you can do midpoint formula if you'd like. So just as a little refresher, you can add the x's, divide by 2, add the y's, divide by 2, and that'll always be your midpoint. Or in a case like this, you can pretty easily count and find the midpoint. So that's probably a little bit quicker. So I think we can all agree that the midpoint's right there. Now that's going to take care of the bisection part. That's going to take care of the bisecting. It's going right in the middle. So now we just have to worry about it being perpendicular. Okay, well, what kind of lines are perpendicular to vertical lines? That would be horizontal. So if I draw a horizontal line going through that midpoint, that green dashed line is going to be the perpendicular bisector of specifically side AB. Okay, now I need to draw another perpendicular bisector to see where they intersect, and then that'll be the coordinates of my circumcenter. So let's start with segment AC here. Again, another nice straight horizontal line just makes life a little bit easier. It won't always be easy like that. Sometimes you have slanted lines, and we might need to go over a problem like that when I come back tomorrow. But let's start with the bisection part. Let's start with the middle. So A to C is 6 units long. Half of that is 3. So if I go 3 units in, that's going to be the midpoint. That's going to be where it bisects AC. And then what kind of lines are perpendicular to horizontal lines? That would be vertical. So I'll go ahead and draw on a vertical line. And I get the question all the time, Miss Kelly, how long should I make it? Like, how long should I draw it? It doesn't really matter, but you need to see where they cross. So you really only have to draw it to the point where they intersect each other. So now you can see those two perpendicular bisectors crossing at a nice even point right here, right? And that's at the point 3, 1. And I think I will do the second one, but I'm going to go a little bit quicker. Now again, when you don't have a nice right triangle like this, or when the sides, I should say, don't line up on nice horizontal and vertical lines, that does make life a little more complicated. But if we have a problem like that on homework, we can go ahead and maybe look at it together. But essentially what that's going to involve is just you're going to have to find the slope of one of the sides and then use the opposite reciprocal slope to draw it perpendicular. Okay, so if I graph one more here, I have a point at -2, 5, a point at -6, 5, and a point at -2, -1. So again, if I was in class today, I would ask you guys to tell me which two sides are going to be the easiest to draw the perpendicular bisectors for, and hopefully you would tell me SR and RT, because those are the nice horizontal and vertical lines. So let's start maybe with SR. Okay, I like to start with the bisection part again. So I like to find the middle points that it's going to go through, and then draw in its perpendicular line. And I really didn't, in my 1st and 7th periods, didn't have any issues with people doing a right triangle problem like this. So regular geometry, this is what will be on your test, I think a right triangle. but honors, you guys might have an obtuse or acute triangle, so just be prepared for anything. Okay, so RT, we'll go ahead and bisect this one as well. There's the middle point. This is perpendicular. Remember, I'm not just drawing it horizontally because it's always horizontal. I'm drawing it horizontal because that's what makes a 90-degree angle with the original line. So it's very intentional. It's not just vertical and horizontal lines randomly. And then where they cross, nice intersection point, is at -4, 2. Now you guys will notice that they do cross right in the middle of the hypotenuse, and that will always happen for a circumcenter. But when we get to the other types of segments and other types of points of concurrency, it won't always be that way. So, I mean, it's deliberate for perpendicular bisectors. Okay. Hopefully you guys are getting a chance to kind of copy all this down. I'm not going too terribly fast. I apologize if I am. Hopefully, if there's a sub in the room, I'll pause the video, let you guys copy this down for a minute. Okay. So the second segment we're going to talk about is the angle bisectors. So the angle bisectors, and I'm not going to go back to the graph and graph them all again, but you'll notice that the angle bisectors also all cross at a single point. But their point has its own specific name, and that's called the incenter. So the incenter is the point of concurrency for 3 angle bisectors. Okay? And for that, those will always meet inside the triangle, the incenter. Now let's talk real quick about what we talked about in section 1. So you have an angle, and you take a ray and you bisect the angle right smack dab in half. Well, we said any point along that angle bisector is going to be equidistant away from the sides of the angle, but only if they intersect at a 90-degree angle, right? So they have to be perpendicular to the sides because that's the definition for distance from a point to a line. So again, now we're just going to take that theorem and triple it because you can have 3 angle bisectors in a triangle because there are 3 interior angles. So in this picture that we're looking at, the actual angle bisectors are the lines cutting through the vertices, cutting the vertice in half, cutting the angle in half. So we have 3 vertices, A, B, and C. A is being cut in half, B is being cut in half, C is being cut in half. Now that does not mean that A, B, and C are equal measures or anything, but A specifically is being cut into 2 equal halves, B specifically being cut into 2 equal halves, and C being cut into 2 equal halves. And they meet at this point P. Well, if you were to just look at angle A for a moment, right, this point P is on that bisector. Here's the angle bisector. Point P is on it. It is equidistant away from the 2 sides of the angle as long as it's crossing at a right angle. We did that yesterday. And same thing over here. B is being cut in half. Meets at this point P. It's equidistant to the side as long as it's at a 90-degree angle. And same thing for angle C. Angle C is being cut in half. Here's a point on it. It's equidistant away from the sides as long as it's at a right angle. So those 3 little blue segments are going to be your segments that are all congruent to each other. Okay, so again, some examples I left off of the notes would be examples like this. P to F is 5, and P to C, I'm just making this up, is 10, and I don't know, B to E is 6, okay? Find P to E. Well, the extra numbers in there, you're not going to use all the numbers, and it doesn't actually take any calculation for this one, but they want you to be able to recognize the fact that the blue ones are the congruent ones, those little, and I always say it's the perpendicular segments that are the congruent ones, and so the 10 and the 6 you wouldn't even use in the problem, they're just kind of there to make sure that you're confident knowing the fact that PE is going to be the same size as PD and PF, okay? Now where we're going to apply this, and again, I think I'm just going to do one example, and I only did one example during class as well, so I'm good with that. We're just going to look at example 3, I believe. okay? And it says that in the figure shown, ND is 5x minus 1. NE is 2x plus 11. Find NF. Well, again, these are angle bisectors, and the reason I know that without deliberately being told is all the markings. So all those congruent markings at angle A and angle B and angle C are telling me that NA, NB, and NC, and I'll just highlight those in red real quick. NA, NB, NC are all angle bisectors meeting at this green point N called the incenter. And they are equidistant away from each side at a 90-degree angle. So those 3 blue segments, and they won't be color-coded, obviously, on your homework, but those 3 blue segments are going to be congruent to one another. And it says find NF. Well, NF is the same size as ND and NE. So if I can find one of those lengths, then I have found NF as well. So I'm guessing most of you might not know you're right, but you might have an idea of what to do here and how to solve for X. Yeah, ND and NE are equal, so we just take those 2 expressions from above, the 5x minus 1 and the 2x plus 11, and set them equal. Can't add them together because I'm not sure what you'd set them equal to if you did, and it has nothing to do with degree measures because they're not angles, but we set them equal to each other because they're congruent segments. So I'm going to go ahead and solve this kind of quickly here. I minus the 2x from both sides, and I have 3x minus 1 equals 11. Add 1 to both sides, and I have 3x equals 12. Divide by 3, and I get x equals 4. Now, the problem is asking for the length of N to F. Well, N to F is the same length as N to D and N to E, so I really just need to plug 4 into one of the expressions. It doesn't matter which one, and that'll give me the length of all 3 of them. So just pick one expression. I think I'm going to pick this one just because it's positive. So I'm going to take the 2x plus 11 and plug 4 in. 2 times 4 plus 11 is 8 plus 11, which is 19. So therefore, NF has to be 19. Okay, and if I were to plug it into the 5x minus 1, I hopefully would get 19 as well. I would. Now this little follow-up question is an interesting question. It says, can NG be equal to 18? So I'm going to erase all my markings up here. Now we are aware at this point, drop my marker, wouldn't be a Miss Kelly day teaching if I wasn't dropping markers. We know at this point that NF is 19 and NE and ND, but that's not important in this scenario. And they want to know, is it possible for N to G to be 18? So think about that for a minute. Some of you might think yes. Some of you might think no. Some of you might not be thinking at all, and that's fine too. And those of you thinking no are correct. It's not possible for NG to be 18. Now let me explain to you why. This right here is a right angle, and I think most of us understand if that's a right angle, then the angle right next to it's a right angle as well. So we are looking at this nice little right triangle made up of NF and G. So I'm just going to pull that out and zoom in on it for a second. And we learned a long time ago, this side right here, which we call the hypotenuse of a right triangle, has to always be the longest side. And just, common logic, you guys, a slanted side is always going to be longer than, in a right triangle, than one of the horizontal or vertical sides. It just makes more, if I was going to walk somewhere, I wouldn't walk at an awkward slant. I would try and get the most straightforward path that I could so that it was quicker. So no, it is not possible for that to be 18 because that's the hypotenuse, and the hypotenuse has to be the longest side. So no, it is not, unfortunately. Oh no, I'm so sad about it, but that's okay. NG is the hypotenuse of triangle NFG, and therefore has to be the longest side. Uh-oh. I also might have spelled therefore wrong. going to double check that before I get off my video. And so actually there might be problems on your homework where you have to solve for possibly something like NG. So just don't forget that it is a right triangle. And so things like the Pythagorean theorem might come into play. Okay, just so that we're all aware. Therefore, definitely has an E at the end. Sorry about that. Kind of embarrassed, but I'm not the best speller. That's okay. So yeah, and then I'm not going to go through the last example because it's essentially the same thing. You just set the two expressions equal, solve for x, plug x in, and there's the length of your segment QP. So I'm not going to go through that. And so just as a little summary here, I always think about it this way. They kind of act as opposites of each other. So the circumcenter, where the perpendicular bisectors meet, and those are bisecting sides. Those are equidistant. The circumcenter is equidistant from each vertex or from each angle. And the incenter, which bisects angles, is equidistant to each side. So again, they kind of work like inverses of each other. If it bisects sides, it's equidistant to each angle. If it bisects angles, it's equidistant to each side. And then also I think about the fact that incenter starts with a vowel, and so does the word angle, so I kind of remember that way as well. But that is section 2 in a nutshell, and if I went too fast, I apologize. This will be online, and you can finish the notes by watching online. So have a wonderful rest of the day. Your homework is going to be the 6.2 worksheet, so make sure you get that completed. Look at your notes. If you have questions, you can come ask me in class or outside of class. Have a great day.